Good day, I'm Norman Wahberger. Today we want to delve deeper into this interesting aspect of these three different kinds of colors in planar geometry. We have three different kinds of quadrances, three different kinds of spreads, and we're particularly interested in how these things interact. And we're going to have some interesting connections with linear algebra today. So our basic starting point are these three dot products that we've defined. We're calling them blue, red, and green, and here are the formulas for them. We also have this cross product, which is a skew-symmetric bilinear form. Okay, so these are all special cases of the more general dot product. The general dot product in two dimensions between vectors AB and CD has this form here. It's the vector AB, the vector CD is a column on this side, and in between a 2 by 2 symmetric matrix. Let's say L, M, M, N. So these two entries are the same. That ensures that it's symmetric. That will ensure that the whole expression is unchanged if you swap these two vectors. Now, if we actually write this out using linear algebra, we see that it has the expression L times AC plus M times BC plus M times AD plus N times BD. So it's a linear combination of these various quadratic products that you can form from the entries here multiplied by the entries here. And you can see that this is a generalization of this here. These are all special cases. In this case here, that would be when L is 1 and N is 1 and M is equal to 0. And similarly for the other kinds. All right, so this is the most general kind of symmetric bilinear form in two dimensions, and we are going to move towards trying to understand what geometry might be like with such a general situation. But for today, we're going to concentrate on these three very interesting dot products. And I might also mention that this topic is overlapping quite a lot with some of the later material in our Wild LinAlg series on linear algebra. In particular, the lectures Wild LinAlg 40 to 42, something like that, are in this direction. So you might want to refresh some of your ideas on linear algebra by consulting and going through this series if you haven't already done so. We are going to move more towards adopting a linear algebraic point of view towards geometry. So up till now, we've kind of looked at geometry classically in terms of points and lines. But it's also powerful to think in terms of vectors and generalizations of that. That's a very 20th century point of view towards geometry, and a very powerful one. The first paper on chromogeometry was my paper called Chromogeometry, which appeared in the Mathematical Intelligencer in 2010. So if you want a reference for this material, you can consult that paper, and you can actually download that paper or read it on my ResearchGate page where you can find most of my papers. It's also on the archive if you have access to that. Okay, so let's remind ourselves about these fabulous formulas for spreads that we have talked about in our last few videos. We have two vectors A, B, and C, D, and here are the three spreads, blue, red, and green. The blue spread given in terms of this kind of expression involving dot products and quadrances. There should be another bracket there. There we go. And then this alternate formula for it involving crucially the signed area of the parallelogram formed by the two vectors, squared, and quadrances on the bottom. And then a similar formula for the red spread, and a similar corresponding formula for the spread in terms of signed area, but crucially with a minus sign. And then a similar formula for the green spread, also again paralleling what's going on here. And then a corresponding formula for it like this one, but also with a minus sign there. So blue, red, and green spreads between the vectors v and u that are in this form here. All right, so these are really basic definitions in metrical geometry in the plane. Going beyond the usual familiar Euclidean story, right? We really want to expand our view of geometry beyond the Euclidean one. This is a fabulous insight of 20th century physics. So we are taking some of the insights that the physicists have. They have told us that relativistic geometry is maybe more in line with the way the world actually is than Euclidean geometry. So it behooves us mathematicians to reorient ourselves so that we are comfortable and capable of working in a relativistic setting. Okay, so we need to expand our point of view, and this is exactly the kind of technology that we need in order to be able to do that. Okay, so we can use those formulas on the previous page to see a lovely connection between the three spreads formed by any two vectors. So if we fix two vectors, v and u, let's say, then we have three possible spreads that measure how far apart they are. The blue one, the red one, and the green one. And these three numbers, s sub b, s sub r, and s sub g, are related by this formula. We'll call it the colored spreads theorem. And it appeared for the first time in my Mathematical Intelligencer paper. It says 1 over s sub b plus 1 over s sub r plus 1 over s sub g equals 2. Okay, so this is really demonstrating that these three geometries are not just of independent interest, they all combine in some fashion. They interact with each other, which is one of the main points of chromogeometry. And the proof is actually not hard because we can just use the expressions that we have already derived. The reciprocal of s sub b will be this expression here. This was appearing on the right-hand side of the equation I showed you before. Now there's the signed area squared on the bottom now, and the product of quadrants is on top. And then when we add these things, we also get these terms here. But crucially with the minus sign here and the minus sign here, because we saw those minus signs appear in the expressions for s sub r and s sub g. So we need to verify that this thing here always equals 2, no matter what a, b, c, and d are. Well, that's a consequence of the following identity. It's actually not too hard to rearrange this because conveniently the denominators are all the same. So if we multiply through by that denominator, the expression to be checked is that this product of quadrances minus this product of quadrances minus this product of quadrances equals 2 times AD minus BC squared, our determinant squared. And this is just a God-given algebraic identity. That's what a lot of these things reduce to. They reduce to just formulas that have been given to us from on high. The nature of the world is such that this is a true fact. Beautiful and lovely, and it's exactly what we need in order to establish this pleasant symmetric relation between the three spreads formed by two vectors. Okay, so let's look at an explicit example, because that's what we like to do here. We like to show explicit examples that illustrate completely what we're talking about, that everybody can look at and verify and check, and that you can also generate similar examples. These are not cherry-picked just to work out. Okay, so let's choose two vectors, say 3, 1 and 1, 4. There they are, v and u. What are the three spreads? Well, here's the blue spread. So it's 1 minus. How do we construct it? We take the dot product between these two things. So 3 times 1 plus 1 times 4, all of that squared. And we have to divide by the product of the quadrances, which are here is 3 squared plus 1 squared, that's 10. And here we have 1 squared plus 4 squared, that's 17. Altogether, we get 121 over 170. And now we can check the alternate formula for that is in terms of the signed area, which is a determinant. It's like an AD minus BC. There it is there. 3 times 4 minus 1 times 1. In the numerator squared, divided by that same product of quadrances, 10 times 17. And you can check that that, yes, does equal 121 over 170. So that's the blue spread between these two vectors. That's the spread that we've been dealing with mostly in this course up till now. Okay, that's the familiar Euclidean spread between two vectors. And it's a number between 0 and 1, because in the Euclidean situation, that's always what happens. We always get a number between 0 and 1, right? 0 here, 1 here, halfway along. What about the red spread between the same two vectors? Well, over here it's the same formula, except that we have to use red dot products. So the red dot product between these two things is 3 times 1 minus 1 times 4. So there will be a 3 minus 4 in the numerator there, squared. And the quadrances down here are 3 squared minus 1 squared, that's 8. And 1 squared minus 4 squared. That's a quadrant of minus 15. So yes, in the red geometry, quadrances can be negative. They, in fact, also can be 0, which is a separate story. Okay, we calculate that. We get 121 over 120. And let's compare that to the other expression for it, which had a determinant squared. Again, the same determinant, 12 minus 1 all squared, divided by the product of the quadrances, same as over here, but also with a minus sign. And that turns out also to be 121 over 120, so we have agreement. And notice that this spread is outside the usual bounds or the usual range for a Euclidean familiar spread. This is a number bigger than 1. It's a phenomenon that we do not see in Euclidean geometry. So if someone came along and said, I have a spread of 121 over 120, we'd know that either they've made a mistake or they're dealing with a different geometry from the Euclidean one. In fact, this is the red relativistic geometry. What about the green spread between the same two vectors? Well, we have to take the green dot product. And that is, well, we have to take this times this, so it's AD plus BC. So 12 plus 1 in the numerator squared. And this quadrant here is 2 times the product of these two. That's 6. And the quadrant of this is 2 times the product of those, which is 8. For a total of 100 minus 121 over 48. And that's the same as our alternate formula in terms of a normalized squared area. There's our determinant, just as in the other cases, squared. There is the product of these quadrances, the green quadrances, and there's that minus sign that we're not able to forget. And that does turn out to be this thing here. And again, we see now a negative number, which is also outside the usual range, but kind of in the opposite direction. Okay, so this is a different kind of spread value that we could see from the usual familiar Euclidean story. So things are arithmetically also a little bit different. We're actually getting different values for the spreads with these other geometries. And let's check that our basic relation, this colored spreads theorem, is true. If we take the reciprocal of these three numbers and add them all up, we're going to get 170 over 121 plus 120 over 121 plus minus 48 over 121. And when we add them up, we get 242 over 121, which is 2. So everything does work out. And the beauty of it is that you can go and check these things yourselves. You can easily just cook up simple triangles. Take that as one vertex and then take two other convenient points with small integer values, and you can compute everything. You can compute the three spreads, the three quadrances in all three colored geometries. You get exact values. You can have a look at what they look like. Okay? This is exact mathematics. We're doing something here that cannot be done with ordinary trigonometry. You cannot do this in ordinary trigonometry. You cannot take 3 points, even simple points with integer coordinates, and actually completely correctly calculate the angles or the lengths, in fact. You can't do it. So we get used to trigonometry being an approximate discipline, which necessarily involves just using your calculator to get 8 decimal places or whatever. Okay? We get sort of oriented to this approximate aspect of making measurements in trigonometry. but it is not intrinsically so. It's because of our misunderstanding of the true nature of trigonometry. It's not meant to be angle-based or distance-based. It's meant to be algebraic, supported by these dot products, the linear algebra that's associated with it, things which are completely computable, completely explicit, and that we can write down in their entirety and admire them. And I do suggest that you do this exercise, get yourself some points and triangles, make lots of computations, see what all the spreads look like in all the different colors, verify the various relationships, and admire the fact that this trigonometry is working in such a wide variety of different situations. It's really lovely. But what does it mean, you might ask? What is a red spread exactly? What are we measuring there? What geometrical picture can we associate to that to have something to put our intuition on? That's an interesting question. And to move towards that, let's start by thinking about the geometrical understanding of quadrances, which are sort of prior things, right? We want to understand quadrances first. And to do that, let's actually go back to our basic blue quadrants. This is the familiar Euclidean quadrants. And just let's think about that from a linear algebraic point of view in a particular way, perhaps a bit of a novel way. So let's look at this quadrant, Q sub b, and here's our vector AB. And I hope you appreciate that this B here is not the same as that B. That B stands for blue, and that B is just AB. These are the coordinates of that vector. So I hope we're not going to be confused. Okay, so the quadrants of this vector is a squared plus b squared, and that's the dot product of these two vectors with respect to our blue familiar dot product. Okay, and we know we can write that in matrix form by having our row vector there, our column vector there, and this identity matrix in between them. Now, a little bit of skullduggery shows that we can rewrite this identity matrix by sticking in this particular matrix and its inverse. Actually, this is not just any random old matrix. This is the matrix that represents our cross product, that skew-symmetric bilinear form. Okay, so we're going to put that in there purposely, and then we're just going to put whatever is required here to make this work. And well, since this is the identity, we have to put the inverse matrix, which is just it's negative in this case. So if you multiply these two matrices, you will get the identity matrix. Now, if we do it this way, then we can lump these two together. We can actually do this product. That'll be minus b, and that'll be a. So this thing here becomes minus ba. And when we write it now like this, we have a cross product because this is our cross product matrix. So we see that we have the cross product between the vector AB and the vector minus BA. And we've seen already that we can give this thing a name. This is V super B. It's a kind of a transformation. It's physically a rotation of the vector through a quarter turn. That's what this superscript B operation does. Going from AB to minus BA is rotating it by a quarter turn in the positive or counterclockwise direction. So when we write things like this, we see very directly that the quadrants is actually a signed area. It's the signed area of the parallelogram that you get by taking the vector v and the vector v super b, and those two vectors generate this parallelogram, which happens to be a square in the Euclidean geometry, because this is exactly perpendicular and because the quadrants here haven't changed. And I'm just sort of noting here that the original vector AB and this rotated vector AB super B, they are perpendicular. And we're representing that perpendicularity by the usual kind of little right angle sign there. But I'm also putting a little b under there because these days there are these different notions of geometry floating around. Right? So there's different notions of perpendicularity. We're talking about the blue notion of perpendicularity here. Okay, so this is familiar, but we want to see how the corresponding situation holds for the red and the green quadrants. So let's play the same game now with the red quadrants. Okay, so let's take a vector AB, the same one, and let's look at its red quadrants, Q sub r. Well, we know that's a squared minus b squared. And that's the dot product of the vector with itself with respect to the red bilinear form, or the red dot product. And we know in terms of vectors and matrices, we can write it like this. Instead of having an identity matrix here, we have the matrix 1, 0, 0, minus 1. Okay, and now we're going to do the same kind of thing as we did before. We're going to arrange that, we're going to write this matrix as a product of two matrices, the left-hand one being our cross product matrix. The skew symmetric 0, 1, minus 1, 0 matrix. Okay, so then we have to think a little bit about what matrix we're going to put here in order that this product be this one here. And you can see that this is going to work because if we take the product of these two matrices, the top entry will be 0 plus 1. Then this entry will be 0 plus 0. This entry will be 0 plus 0. And this entry will be minus 1 plus 0. So that does work. And then we're going to do the same thing as before. We're going to take these two and multiply them, giving us BA. So this product becomes BA. So the original quadrants can be rewritten. Instead of having a symmetric matrix in there, we've kind of transformed things. So now there is a skew symmetric matrix there, our favorite skew symmetric matrix. And to compensate, well, now we no longer have AB on the right-hand side. We have this other vector, BA. So we can interpret this now as a cross product. It's the cross product of AB with BA. And when we have a cross product, we have geometrical intuition. That's telling us that is a signed area of a parallelogram. So there's AB. Where is BA? Well, here it is right here. There's BA. It's the reflection of AB in this, this line here, the line y equals x. Or actually, you could also think of it as being a kind of a, well, in this case, it's the reflection in this thing, but in other cases, you might also want to reflect it in this thing here. But in this case, it's a reflection in this line here, and there's BA right there, and we're going to give it a name. We'll call it V super R for red. So we now have an interpretation of the red quadrants as being a signed area of a parallelogram, but in fact, this parallelogram perhaps deserves to be called a square in the red sense, because these things here are actually perpendicular in the red setting. And how do we check that? Well, if we take the dot product, it's this times this minus this times this. So the dot product really is 0. That's what we mean by perpendicularity in the red geometry. So it's exactly the same picture really as in the blue setting, except that we have to modify by thinking about our other kind of geometry that we're using. We still end up really talking about the oriented area or signed area of a red square. That's what the red quadrants is. So the quadrants, the red quadrants of that vector there is the signed area of that red square built from that vector by this kind of perpendicular rotation / reflection vector that we get by reflecting, in this case, in this line. So naturally enough, we want to do the same thing for the green quadrants. So let's look at the green quadrants of the vector AB. That's 2AB, and that's the dot product, the green dot product between the vector and itself. We can write that in the usual matrix fashion. There is the symmetric matrix corresponding to the green dot product. And we're going to rewrite it by writing it as a product of our cross product skew symmetric matrix times something else. And you can check that the something else is this thing here. And so then when we multiply these two things, we get minus AB, allowing us to rewrite the green quadrants as the cross product between AB and minus AB. That's the reflection of this vector here in this line here, in the vertical axis, the y-axis. We're just negating the x-coordinate. A goes to minus A. So we could call that, if this is V, we could call this V super G. Okay. I have to remark that this particular choice is a little bit different from the choice in Wild Linear Algebra 40. So if you're interested in these things and want a little bit of more information, check out the videos around here. But there I use the negation of this thing here, which is the reflection in the x-axis. Okay, one could also define it this way, but in order to be consistent with what I've been doing for the other ones, so that we get V cross V super G as the signed area or quadrants, this is a convenient choice. So here's the definition, that AB super G is minus AB. And we can check that, yes indeed, these two vectors are perpendicular under the green perpendicularity. So we could identify that this is actually a square in the green sense. So we could put a little square indicator there and maybe a little G telling us that's a perpendicularity there in the green setting. So this is actually a green square. The quadrants of these things are equal and we have perpendicularity there. In fact, you can check that there's perpendicularity at all of the four vertices. And we have exhibited our green quadrants as a cross product between AB and this other vector. In other words, as a signed area of that associated parallelogram or green square. So let's summarize what we've learned in a theorem. Let's call it perhaps the quadrants as signed areas theorem. And it's telling us that the blue quadrants of a vector is the vector cross V super B, where V super B is given by this formula. The red quadrants is given by V cross V super R, where AB super R is given by that formula. And the green quadrants by V cross V super G, where AB super G is given by that formula. And so these are transformations of vectors, blue, red, and green. We might call these things the blue, red, and green perpendicularities. That's a name for going from V to VB. We call that a blue perpendicularity. Okay, so these kinds of things are discussed more in my Wild Linear Algebra 40 to 42 series, and so you might want to have a look at those. So we're now in a nice position, so we can now go one step up. So having understood the geometrical content of our three basic quadrants in each of the colors, we can now talk about the three basic spreads in each of the colors. And what do those things really mean? And we'll see that we have a very nice, attractive, geometrical way of thinking about what each one of these colored spreads really means. So we'll do that in our next video, and I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.